will I be okay I erase this portion? Because before I barely use slides. Actually, I don't like to use slides. But right now I'm using slides, and so the page will be a little bit faster. So when you take notes, if you don't print out this one, you have to write very quickly. If you have the kind of printout or like the tablets, you can never write it on that one. Okay. So for this case, let me work on this one quickly. So this again, we have So now for this one, from here we look at the system here, and here the U is the input force. So sorry about this kind of the symbols. And here for this case, I believe U is certain kind of the given the loading, okay, which is one of the external loadings. Here is a U. And here we have two mass blocks. So for each mass block, we assign a degree of freedom, x1 and x2. So for this one, it's called the two degree of freedom systems, because here we have 2 degrees of freedoms. And so for this case, this is a wall. So the modeling can be done by this. So first one, we simply take the free body diagram on individual mass. So let me take this one first. Okay, on M1, we have the external loading. So let me write it up quickly. And let me take here. M1 and M2. So if you would take the notes, for the things, spend your whole line of your notes. And on M1 here, we have the given loading UT. Let me write it up here. Okay, so now again, assume in my modeling, I will assume x2 move is larger than x1, and that'll be easier for us to find out the directions of this. Okay, now from here, let me work on this one. Due to displacement, degree of freedom assigned and moving rightwards. So from here, the spring K1, based upon this configuration we assumed, that will be stretched. So that means it's going to provide a recovering force in the opposite direction, and that one is equal to K1 times x1. Okay? Okay, and now for M1, I want to consider the influence of this. For that one, for that spring, you can see right now the x2, based upon my assumption, x2, this point is moving larger than this point. Basically, this spring has been stretched as well, right? So that means the spring has been stretched, then it will have the force to pulling, and that is equal to the spring constant is K2, and magnitude is S2 minus x1. And the same thing for the damper, and damper is B, and x2 dot minus x1 dot. Be good? Okay, and on the other side, for M2, you can see for this spring, this basically respect to this point, this force is the action reaction. Is an action reaction to this point. So basically on the other side, this one is a reaction force, which means has the same magnitude, opposite direction. So here this is K2, x2 minus x1. Okay, so the same thing here. We have B, x2 dot minus x1 dot. Okay, so now we have done this, and then eventually now we're going to go for that one. So for spring K3, and K3 has been compressed. And compressed, that means if the spring has been compressed, then basically going to bounce back, so the spring force will be K3 times X1 in these directions. Okay, so now by using Newton's law, basically this one equal to m1 times x1 double dot in that directions. And this one will be equal to m2 x2 double dot in that directions. Okay? Because here, why in this direction? Because that direction is to align to the direction we place with from here. Okay, so that's the initial force. So right now for here, for this equation here, then if we take this positive, then m1 x1 double dot will be equal to, we write it about 1, 2, 3, 4, totally 4 terms. So we simply write it up x1 and minus k2, x2 minus x1 minus b, x2 dot minus x1 dot. Oops. I made a stupid mistake.
KX2.
This must be plus, right? Yeah, because they are in that direction. So positive direction. Okay, good. So in this way, this term will be equivalent to, after the arrangement, it will be equal to this term here. The same thing for these equations. And you have a rank x double dot will be equal to minus k2 x2 minus x1 and minus b x2 dot minus x1 dot and minus k3 x1.
Should that be x2?
K3x2.
K3 x2. Thank you. Sorry, typo. Okay, so this one will become this one. So again, here you can see, here I have K3. Oh, that's okay. Yeah. Okay, so basically this equation will be equivalent to this one. And once we have the two equations, and this semester I will not to talk about the state space. So this is called the state space representations. Okay, in this form. And here I can quickly show you how to do it, but you don't need to worry if you wouldn't be able to get it. Okay. So for the state space representation, basically here is we try to represent the result in terms of the degree of freedom, and arrange the degree of freedom in terms of the linear space. So right now for these examples, we have a degree of freedoms, and and that means x1 and x2. So x1 and x2, that in physics, in mechanical system, it's called the degree of freedom system. Degrees of freedom. In controls, we simply call the state. So x1 is one state, x2 is another state. So for this system, it's called the two-state control systems. Okay. So in this way, we arrange the state in terms of the column vectors. And because these are dynamic systems, and we have a state also first derivative of the state and second derivative of the state. Okay, so right now we have things aligned, and then we try to build up this equation first into that form, and right now we want to convert this one into the algebraic form. Algebraic form is this. You know, if say ax, and let me do this one. So ax, say for example, if a equal to a11, a12, a21, a22, and for example x is 1, 2. So basically in this format, this one representing the two equations. And that equation is first row multiplied with this column, a11 times x1 plus a12 x2. That is the first equation. The second equation is described by this row multiplied with state a21 x1 plus a22 x2. Okay? So if we reverse the process, we have the two equations. Are you able to write it up in this form? You just reverse it. Okay, so we do this one by one. Right now we have these equations, and right now here, let me lay out the information. So here we have the blocks. Okay, let me put down the blocks first. Equal to blocks. Okay, now for this term, m1 times x1 double dot. This row multiplied this column must be equal to m1 x1 double dot. So m1 is here. This one is 0. You good? Okay. And how about this one? B x1 dot. B x1 dot. So that is B is here. Okay. And then B minus x2 dot. So that is, oh sorry, this is 2. So this is minus B. Okay. And so we done this one. And now for this case, k times x1. So k1 times x1. And then again, the k2 times x1. So k1 plus k2. So that is this term. And then minus k times x2. So this is minus k2. Be good? Okay, and then that one will be equal to 0. Then for the second equation, the same thing. Now the second equation is m2 times x2 double dot.
U instead of 0.
Oh, sorry. Yes, that's the issue. For the second one, that is x2. So this row multiplied this will be m2 x2. So m2 is here. This is 0. Okay. And now for this one, bx2. So this term multiplied with this must be equal to bx2, so b is here. And then we go to the second term, b times minus x1. Okay, so this one multiplied with this, so the minus b should be equal to here. And now for x2, it is k2 plus k3. So again, this term multiplied, the row multiplied with this must be equal to k2 plus k3 times 2. So k2 plus k3 should be go to the second positions here. And then for the final one, minus k2 times x1. So this row multiplied with this one is minus K2, so minus K2 is here. Okay, and this one is 0. So now we obtained is this one. So this one is called the state space representations, and yeah, they should be supposed to be a linear system. So here I want to exercise more on this one. So for this example, I think these have the numbers, and that was pretty much similar to your homework. So you might be able to give an exercise with the numbers, and the procedure is the same as before, and so I will leave it for your exercise, okay? And now we go to electrical systems. Electrical systems basically is a quick summary, very basic, very fundamental electrical system that most of things you learned from M307, and I've heard 307 is not fun, right? 8 o'clock, and then, but anyhow, this page summarizes the basic components we're going to use. On the this side, basically here is the rule for the passive components, resistors, capacitors, and inductors. This is the equations relating the current and voltage driving force called the EMF between those things. So the voltage driving across the two terminals basically equal to Ri. And for capacitors, you must have the oscillation of the voltage and to produce current. If this is a DC, basically everything will be dead, the stationary. Okay, and this one basically will depend on the time varying current and have the voltage produced for inductors. So that's the three basic components. And the rules for us to formulate the circuits, the equation from the circuit are the two. One is basically called the Kirchhoff principles, and one is on the current. At any node in the circuit, there's no accumulation of the current. So that's the first rule. So that means how much you get in, how much you must put out. Okay. And the second one is the closed loop about the voltage. That means in a closed loop, if you follow a closed loop to the original, to the place you started, basically you accumulate no voltage. Okay, so that means you follow up a circuit, closed loop circuit, basically you gain nothing on the EMF. Okay, so that is the two rules. And based upon the 5 elements, we should be able to easily figure out something. You still, the first one, we look at this simple RC circuit, and basically RC circuit is provide some kind of oscillations. For example, we apply the passive components Ri, and that is the voltage across the 2 points. And this represents the voltage across the points. Basically, from here, if you follow up this loop, then basically the VI equal to the two things. And also, you look at from the output terminal V2, this point. If you follow up this closed loop, this voltage must the drop in the tube between the 2 points must be equal to this one. So we have this. Okay, so if you like to visualize V2 as the terminal, V1 as another terminal, basically you can, based upon the two equations, then apply Laplace transform. Okay, Laplace transform is this. If you remember any integral, taking the Laplace transform, if you still have that table, we haven't exercised this much before, but this one basically equal to 1 divided by s and times of s. So assuming the Laplace transform of f of t defined by f of s. Okay, so this one should be the first time, I think, first time we've seen this one. So again, the Laplace transform of any integral functions If F is eligible for the Laplace transform, then that is 1 over S. Okay. So with the two equations, then how to simplify the form? Basically, you can take advantage of the Laplace transform on the whole two equations. Then you should be able to easily to find the relation, assuming this is output, that is input. Then you can have the transfer functions, and which is describe the function between the output input, and that will be this one. Okay, and RC 1 over S. So in here, say for example, if let me give one example here. So if we want t equal to say delta t. Delta t, what is delta t? The impulse, right? Basically, that is in electrical, they have a term for the spark. You should get a shock. Okay, basically they provide a shock signal there. So in this way, the Laplace transform of the V1 will be equal to Laplace transform of the delta, and that is equal to 1. Okay, under this situation, you should be able to calculate V2. So V2 will be equal to 1 RCS plus 1 times V1, and V1 equal to 1. So basically equal to RCS plus 1. So this is V1, V2. So V2 over T basically is the Laplace inverse of RC as plus 1. Okay. And if you remember again, we have is A as plus 1, and that one corresponding is E minus AT. That is the plus the tables. So from here, this one will be equal to E minus RC T. We good? Okay, so once if we provide here is the impulse signal here, then you're going to measure from oscilloscope. Here will be the signal. That signal will be starting is you get the impulse and then you decay quickly. Okay, and then if we give say another example, if V1 equal to unit step input, from the beginning you just provide a constant voltage. Say if this will be the any toys, you turn on the 3 volt or 5 volt voltage. Basically, that in this case. Eventually, this one you can calculate the VQT and see what happens. Okay. So next time we come back, we'll continue from this onward.